Okay, this session is going to be about cloud computing. I'm going to talk about what the impact of the cloud is on your application. So the goal of this session is obviously to drive you away from the cloud. So that's all mine, right? No, that's not the intent. I'm going to show you what the cloud is about, how it works, what the downsides of it are on your application, but also how to fix it and how to thrive in that environment. That's basically what this session is about. A short note about myself. I'm from Belgium. My name is Yves Goeleven. Udi likes to call me the cloudy Belgian. I'm still not sure if that's related to Windows Azure or the fact to how much beer that we drink. It could be either. But anyway, I've been involved in cloud computing since 2008, mostly on the Windows Azure platform. I'm also Microsoft Azure MVP. That means that anything positive I have to say about it is not true, right? It's just my Kool-Aid. But on the one hand, I'm also in a very special position with regards to particular software. On the one hand, I'm a part of the team. I'm a developer for the engineering team. But on the other hand, I'm also running a service on top of it. So I'm also a customer. I'm eating my own dog food, basically. Right? So that's the way I learn most about it. This talk is split into 5 parts. Actually, it's 3 parts. First part is giving you a big understanding of the cloud, how it works internally. So I give you some internal insights about Microsoft Azure. Then I will cover 3 of the issues that you will eventually meet when deploying an application there or when running there. And then finally, we'll look at what you need to do and how Service Bus can help you to overcome those 3 issues. That's the cause. So the understanding. First of all, we want to have a look at why people are actually interested in the cloud. They don't just go because Microsoft sales, they tell you to go. There are actually benefits in going. And the most important one that I see in practice is automation. We've seen it in the previous talks already, how important automation is becoming in our environment. And the nice thing about cloud computing is that it automates everything, starting from the hardware up to deploying your software all in one go. The most extreme examples are, for example, Windows Azure websites that even integrates with GitHub. You can just do a git commit and it will automatically compile your code and deploy it into your production environment. That's the extreme case. So automation is a very important aspect. One more is scalability. It's very easy to ramp up more resources. Right? It takes you 5 minutes to launch a server. It takes you about the same time to launch 10 servers. If you need them, you can get them, just a single click. Elasticity is also very important because many different use cases only require a certain amount of resources for a certain amount of time, and afterwards they want to let go again. If you want to do the same thing on-premise, you will have to provision for maximum capacity, and the rest of the time you will actually be wasting those resources. This then ties into with the 4th point. Cost is a very important factor for businesses. The fact that you can scale down will also drive your cost down, but also some aspects like, for example, storage are radically more cheaper in the cloud than they are in your own environment. And then finally, I don't think it's that important here in the US, but it's very important for European companies, is that you can automatically go globally. Belgium is like the size of Maryland, I believe, in size. So if Belgian company wants to set up a data center for other countries, it's very difficult because the legislation is different between all the different countries. And the cloud actually allows us to do that without all that hassle. So, what is Windows Azure? Well, Azure is actually the cloud operated by Microsoft. Currently, it consists of 14 global distributed data centers. These data centers are huge. They're nothing compared to what typical organizations have in-house. I will show you a little bit later. And on top of those data centers, there are also services running. Services that you can use in your applications and that you will probably use in your applications when you're also hosted on Azure. So it's also something to take into account. I'm not going to cover these except for the services that we use inside Service Bus. I will talk a little bit about them. And this is an example of such a data center. This is the Dublin data center while it was being constructed. Here you can see it while the roof was still off. what you see here at the top is actually the air conditioning system of the first server room. Okay, there are 3 of these rooms in this building. At the day of speaking, there is one more building of the same size behind it, and then there are even more servers outside in the field. Right? These are in a container. So all of these servers are actually built up of modular blocks. Well, this is an example. Every data center has been constructed differently, but this is one that could be positioned outside. So it's a sealed container. Inside you can find 2,000 to 10,000 servers, depending on the size of the container, and it's completely standalone. So this one is air-cooled. If you have the ones in the south of US are not air-cooled, right? That doesn't make sense. It makes sense in Dublin to do it with air cooling. Other data centers have other hardware and other cooling systems associated with it. So in this one, you have all of this hardware inside. It's commodity hardware. It's intended to break, right? And the container is actually managed as a single unit of failure. It has 3 plugs for electricity, power, and network. And these units are actually managed as a whole. That means if certain amount of servers breaks down, they will not go in and they will not replace them. It takes up to, I think they will replace the entire container at about 30% capacity left. Then they just pull out the container, put in a new one, and hang it into the system. Okay. So this is another type of data center than what you are used to on in-house. Today, these data centers look a little bit like this. You have the top of rack, the racks, and you have switches. That's about it. And everything is wired together in all different ways to actually share the entire bandwidth of all of the components. With this architecture, the generation 3 one, we can support in one data center up about 100,000 physical servers, and the entire shared bandwidth is up to 5 terabits a second. Okay, that's inside the data center. Do not think, please, that you can have access to 5 terabits a second. Right? The individual machines, which are actually virtual machines, will be hosted in these physical machines and are artificially throttled. Okay, that's something very important, the artificial throttling. I will come back to that later. It's a very important concept in the cloud. I think this morning Ted also spoke about the fact that if you deploy to the cloud, they're actually continuously shoveling the infrastructure underneath you and moving you around. That's actually happening in Azure as well. So older architectures look a little bit like this. First generation in 2008 was more based on a north-south architecture, especially targeted web traffic. But after a while, they started noticing that the services internally are more talking to each other than the users from outside are talking to the web services. So they noticed that the shared bandwidth, which at that point was only 120 gigabits, was actually way too low. So they quickly shifted to generation 2, which is similar to what they have today. But it also ran out of capacity at about 30,000 servers. So they had to scale up, and that's why they are at generation 3 now. All of those changes are continuous. Okay, they're continuously changing the network. Generation 3 is definitely not the last one. They will have to increase their capacity. So whenever you're running there, they're actually changing whatever is underneath you. Okay, that's important. It's very important to realize. It's different from home. But in any case, all of these architectures are logically structured the same for management purposes. And these things are called clusters. And clusters are a group of racks that together make up about 1,000 nodes. Those are physical servers. Right? And all of them are one fault isolation unit. Okay? If it is possible that all of those 1,000 servers go down all at the same time. Okay, but it's not possible that for hardware failure that another cluster is also going down at that same point. These clusters are managed by something called the fabric controller. And the fabric controller is actually responsible for managing both the hardware and the software. So both the hardware provisioning as well as the software running on top of it. This fabric controller, you can compare it a little bit to the kernel of your OS, which is also responsible of managing the hardware you have in your server, as well as the software that's running on top of it, all of the threading cases. Same thing is the case here, but at a very much bigger scale. So it's across the 1,000 servers that's actually responsible. Okay, that means that if they shove in a new container to be used within a certain cluster, those containers are actually bare bone. There's nothing on top of them. It's the fabric controller that's responsible for grabbing the hardware, making sure it's compliant to whatever Azure requires, and then also putting your software on top of it. It's fed by two different directions for that reason. On the one hand, it gets a gigantic XML file from Microsoft that describes all of the hardware in its cluster. And that are all the details, so even IP addresses, etc., is all in those XML files. And on the other hand, it's also given an XML file by you. Whenever you create an application in Visual Studio or you create a VM to be packaged and to be hosted in the environment, it will be accompanied by such an XML file, which describes what the topology is that you need. And it will combine those two XML files and figure out what it needs to do to actually host your application on the available hardware. So this is a long process. It's called a deployment process. I'm going to explain to you in very high level view how it works, not too many details. If you want to have more details, there is a great talk by Mark Rusinovich online that explains everything in detail. Okay. So basically what typically happens is you create a service package in one way or another. Usually when it's us developers doing that, it's in Visual Studio. We have these cloud services projects. And in those projects, we actually create an XML file. Right? It's the project called Cloud Service in which you have a web and a worker role. Those things are actually settings that will end up in such an XML file. That is uploaded together with your code. And the Azure system will actually look inside of the XML file, what do I need? Okay, and it figures out, it starts allocating resources based on what your requirements are. So if you say in that XML file, I would like to have 2 times 1,000 machines, then it will have to start figuring out, how am I going to give this customer 2 times 1,000 machines? And that's the service allocation process. It's actually quite complicated because it has to take a lot of things into account. One is the available hardware, or at least the hardware that you require versus the available one. This has to be done at the CPU level, how many cores you want, as well as at the memory level, how much memory do you want across your different nodes, how much storage do you require, and what are your network requirements. All of these things can vary, and you can actually control them in some extent. Right? There are some tricks and tips that I can give you outside of the presentation on how to optimize all these. But that's not the only thing that it needs to keep into account. There's also a concept called fault domains, because each cluster is a fault unit on its own. It can actually die if the top of rack router goes down. Okay, so if you instruct it to have your application on with an SLA, it has to make sure that those resources are across different clusters and different fault isolation units. Next to faults that can mess up your system, there is also an upgrade process going on. When Microsoft wants to upgrade the host OS of the machines, it will have to take your VM down to be able to actually deploy a new hotfix or whatever it needs to do. But it cannot take all of your VMs down at the same time. So orthogonally on the fault domains, there is also something called an update domain. And within these update domains, Microsoft ensures that if you have 2 nodes running, it's only going to take 1 node down until it's upgraded before it starts taking the next one down. Okay, so this is at 2 levels that it has to keep these reasons of downtime into account, both faults as well as updates. And then there are, of course, there are secondary goals. One of the things is users like to have as low latency as possible. Okay, in a data center this size and you're a football field away from each other, that would introduce a lot of latency. So the fabric controller will try to put your nodes as close together as possible. with keeping the primary constraints into account, of course. And furthermore, it will also try to take into account the speed of the upgrade process for Microsoft internally. Depending on how it positions the VMs in the data center, it will be easier to guarantee the update domains or not, making it slower or faster to actually upgrade the entire system, which has to happen every now and then. So it figures all that out, it performs a compilation, and then it chooses a certain amount of machines in the network. Right? They may be available as already pre-provisioned host, or they may not be available. It might be just raw hardware sitting there. So what it actually needs to do from time to time is actually grab a piece of hardware and make it compatible with Azure. And that's what is being illustrated in this picture. So it actually will physically power on the node. It will then PXE boot into a maintenance OS. That maintenance OS will format the disk, download the ISO of the host OS, start installing that, reboot, do a sysprep, and then it will only start installing your guest OS. So there's quite a lot going on. It might be completely provisioning the hardware, as well as completely provisioning the guest VM that your application code is going to be running. And it's doing that all in like 9 to 10 minutes. Okay, so if you just think about what's going on in the backend, it's actually quite impressive. But if you're looking at the Azure portal and you're hitting F5 to see your node come up, it might feel a little bit slow. Okay, so it depends on how you look at it. So once the machines are provisioned, it will actually put them in the network. Okay, so it will internally configure the network. It's not publicly configured yet, but internally all of the different machines can already talk to each other. Once that happens, it will actually add your code to it. It will deploy your application or your service, and it will make sure that runs. You can do whatever you like here, okay? So it's important that you know that you have administrative rights at the time that this happens, and you can install whatever you like, okay? If you want to host JBoss or whatever inside of it, go ahead, you can do that. And once your application is up and running, then it will configure the public-facing network parts, meaning the network load balancer will be configured to actually route traffic to your nodes. Okay. Here it's just drawn for 4 nodes. It can do that up for 1,000 nodes, whatever you can afford. Okay, so that's your only scalability limit is your wallet. Okay, so what's important in this environment is that failure is actually pretty normal. I told you the machines have been designed actually to fail. It's a container with some small spec machine in it. It will die. Okay, that's expected. Now, the environment will always respond to it in the same way. It's a load balancer that detects that a machine is not reachable anymore for any given reason. It will tell the fabric controller, and the fabric controller will say, well, let's forget about that machine. Let's give him a new one. So it will always start from scratch. And this has very important implications for your application. So the implications are the machine failure in itself is very normal. The machines on their own are very small, have low specs. Do not expect a lot of power from an extra small instance. And there is also little to no redundancy in the machines. There is no double power input. There is no double disk. No. It will just die if it dies. So the system is always in a partially broken state. And the system will therefore provision clean machines for you. And this can occur at any given time. So there is no SLA that says it cannot go down the machine inside the business hours. Now, there is always somewhere business hours for somebody on the planet. In a global system, this is impossible. So any kind of upgrade, either the host upgrade, your upgrade, or any kind of failure, either the hardware, the host VM, the guest VM, or your code, whatever, it will take it down, give you a new one. Okay? Moves are treated the same way. If you want to move, you can ask this at the help desk. If you want to move a machine from one account to the other, it will simply spin it up there and take it down there. Okay. Implications of this are, for example, very nice side effect is that you always lose the data that's on your disk. That's very important because if you have a database on there, too bad, the database is gone. Okay, so that's something that you need to keep in mind. How do you actually handle all of this? Well, you write your application in both a distributed and a duplicated way. That means that if you would compare this in service bus terms, that you create multiple endpoints and you host every endpoint at least twice. Because it's very likely that one of the machines that's hosting one endpoint is down, and then the other one can actually stay up. 2 is the least that you have to do. 3 or 5 is better. Why 3 or 5? Well, because you have both fault domains and upgrade domains. You can have a failure during an upgrade, and then it's better to have 3. Okay? You don't have to do that, but your SLAs will be better. You also have to accept that when communicating from machine A to machine B, that machine B might not be there. I think for this audience, it's quite clear what you need to do, right? You stop thinking RPC style, and you start doing messaging based on queues, right? In that situation, both machines don't have to be up while they're talking to each other. And furthermore, you should also not put anything on the disk. Put it somewhere else. Right, there are a few services that are good at this. For example, Azure Storage Services are specifically designed for this specific use case. Okay? Don't put it locally, put it remotely. It has downsides because you're using a service, and I will talk about the other downside of being a service later. But it's better than putting it on disk. And if you put it on disk, make sure it's also somewhere else, that if you can bring the disk up again on another machine, and you copy the data from that other location. Okay, so you can still use the disk as a cache, but do not treat your disk as the single source of truth, because that will actually disappear. This is not going to happen every day. It's like once a month or maybe once a year, depending on the quality of the hardware that you're on. But it's guaranteed that it will happen. You will lose that disk. Okay, second issue, size. These data centers are enormous. I've been there. You can actually visit them as a tourist. I will take you on a guided tour. I've been able to see 1/3 of the first building of Dublin. Okay, so there is quite a lot. If you want to think about the size, there are 13 regions, it says here. Actually, they just announced the 14th in India today. So now there are 14 regions. In those 13 regions, there are 321 IP ranges, more than 250,000 customers, and more than 2 million VMs hosted on all of those physical servers. I know applications that take up 300,000 servers on their own. Right? The most popular games on this world are actually using so much servers. And inside of the storage system, there are today 25 trillion objects. Well, at least more, because these numbers are, I think, already a few months old. But it gives you an idea. This is not something that's comparable to the data center that you have at your location or at your customer's location. Usually not for the big customers either. So the implications of such a huge network is that latency is actually very, very normal. Okay, I/O is typically the bottleneck for your application, especially because you're not going to put anything on that disk. You're going to do everything outside of the server. Okay, so outbound I/O, I typically see that as the limiting factor for my application, something you need to take into account. And furthermore, network partitioning is also happening all the time. So if you have 3 servers, it could be that server A can talk to B, but C cannot talk to B, while A can talk to C. That's perfectly possible. Okay? This is also the reason why distributed transactions are either very flaky or not supported at all. Okay, I think you can technically set it up yourself if you want, but it's highly discouraged, because in the distributed transaction, every node has to tell every other node that it's done, and then actually talk back to commit the results. If one of those links is broken, the distributed transaction will time out or roll back. It will not succeed. Okay, so typically it doesn't really work, the distributed transactions. Now, how do you deal with all of this? Latency is typically dealt with working on multiple threads at the same time. Meaning, you do an outbound call, you let one thread wait for that call, and you spin up another thread for continuing working on the server. Okay. Don't overdo this. I've seen this a lot, that people use async await framework and then take their thread pool and pumping it up to 1,000 minimum threads. It's not the way to go. Okay, these are very small machines typically, and you'll easily take them down. So tune down. It's better to spin up more machines in parallel that all have, like, say, 12 to 24 threads per core, and work in that way instead of trying to squeeze everything out of a single machine. The lack of DTC. Well, we typically handle that the same way as that Jimmy explained earlier when he was working without the transactions. Right? We use compensation logic. We use atomic operations where possible, and we make sure they're idempotent as well. Okay, that's something that you need to keep in mind. Okay, third aspect, the fact of being a service. Right, this is something that many people overlook, and I want to emphasize it a little bit. You get about 200 different services on the Azure platform. Whenever you build applications, it's in your benefit to use them because it's code that you don't have to build. But it also, at a certain point, is going to work against you. Okay, you have to take that into account. So that is, so a service at the outside, it looks like a product. SQL Azure looks the same as SQL Server from the outside. You can talk SQL to it. It has all the same features. So many people start treating this thing as a SQL Server. They will just take that existing entity framework or an Hibernate code or whatever they have and try to port it. And then they notice that SQL Server Azure is going to push back on you. Right? If you ask it too many questions, too many queries at the same time, it's going to say, no, I'm not going to answer. Come back in a second. Okay? So it's going to push back. This has a reason. Right? The SQL Server or the SQL Azure is actually not maintained by you, but it's operated by the vendor. The vendor has different targets than you have. Okay, it wants to serve as many possible customers with as little resources as possible. Okay, so these environments are typically shared hosting, but it wants to ensure that everybody gets the same piece of the pie. If this guy can do 300 queries a second, the guy next to it should also be able to do 300 queries a second. Okay, makes sense. So it will actively cut you off at a certain point to guarantee that the other guys are also getting their capacity. Even if in the background it has a lot more capacity, it is still going to block you because you've got your share. Okay. They also operate on a lot lower marginal profits. So the price that you pay per unit is actually a lot lower. This is true for SQL Azure. This is very true for storage. Right? This is really cents per gigabyte that you pay. It's really nothing. And it also means that there is a big difference between the capacity that you actually could be using at a certain point in time versus what is actually provisioned at that certain point in time. They have to keep their cost down as low as possible. If you say, I want 50 terabytes of data space, but you're only using 1, they are not going to allocate 50, even though you are committed to get 50. Okay? So they will provision less than what you actually asked for. This has some serious implications, and one of those serious implications is that the individual resources on their own are always very limited. Okay, where you, for example, have a local Amazon queue, you can easily push 5,000 messages a second to it. If you take a similar queue in, for example, Azure Storage Services or an Azure Service Bus, you will never get to 5,000 for each queue. Okay, you might get 1,000. But on the upside of that, in the Azure platform, you can ask for as many queues as you like. One namespace in Azure Service Bus, for example, can have 10,000 queues in it. But you can have 50 namespaces if you like in your account. And you can have as much account as you like. So you can always get more containers with more resources. You get less individual resources. One queue is always less than what you would have on an on-premise variant, but you can get more of them. Each of these resources is also artificially throttled. So if you try to push or query SQL Azure too much or try to send too many messages to an Azure Service Bus queue, it will push back on you. It will give you an exception and tell you to come back in 30 seconds. Okay, that's very different from what you might be used to your local database. Your local database either works or it doesn't. And here you have the step in between where it does work, but it refuses to serve you. Okay, that's throttling. Your resources are also being moved around all the time. So if you have a queue, for example, in Azure Service Bus, and your node that you're on is very hot, they will start splitting that out across multiple nodes. That means they have to physically move your resources to somewhere else. During that time frame, they will also push back on you. It's like, we're moving you, okay? Come back in 30 seconds. They will do the same thing. This will all result in different types of transient errors. These are not bad. Right? They just tell you, try again in 30 seconds. Trying again is very important. A second big aspect of having these services is that these services will almost never allow you to grab a lock on the server side. Because a lock will hold on to a certain amount of resources. And if you can just grab as much resources of those as you can actually take the system down. Okay, they don't want that. They want to be fair to everybody. So they either give you a very short lock or no lock at all. And this also has the implication that local transactions typically are not supported. Okay, where you are used to having a local transaction in your SQL database, Azure Storage is not supporting any form of transactions at all. It's transactionless. The same with Azure Service Bus. It is, at least on the outside, it is transactionless. Okay, so we live in this very same world as what Jimmy was talking about earlier. We live in this transactionless world. Okay, nothing is guaranteed. One exception that's interesting is that the SQL language on its own has this transaction concept, and that is supported. So SQL Azure is one of the exceptions to the rule. It will have local transactions available for use. That's why the SQL transport is also very interesting in Azure if you have to port an existing application, for example. Okay, so how do you deal with this? Well, in general, the rule is try again. And be very persistent about trying again. Just retry, 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 retry. Okay. And if that didn't work, back off for a while and then retry again. And hang on. Okay. Only if it's really a bad exception, then you fail. But typically you don't. The lack of local transactions. Well, you combine this retry mechanism with atomic operations. You try to be as atomic as possible. And if you can't, you use compensation logic, often derived from the business that you're in, to actually deal with this. Important in this case is that you need to take care of idempotency. Okay, there's no way that we at Service Bus can actually handle the idempotency, because it's the transport itself that is going to resend you the message explicitly. It's not something that is conditional because you have transactions off. No, it's after a certain timeout period, it will send it again. And it might be sending it to another instance of your endpoint. So you can have competing endpoints having the same logic running at the same time if you don't watch out. Okay, so we cannot take this away completely. We do our best to limit it as much as possible. But if we cannot cover it always, okay? So you have to, in the majority of cases, you have to work in an idempotent way. Okay, so how can Service Bus help you thrive in this environment? Because it looks very scary, all these changes, this is all very different from what you might be used to in a smaller network. But actually you can live in this way perfectly. There's no reason why you should not be able to overcome all of these issues. Now, so how do we overcome? Well, the first quick fix, or the quick win in this case, is that messaging itself solves a lot of the flakiness of the platform. Machines can go away. If you have a queue in place and you have a messaging concept, that's fine. Okay, the machine can go down and be brought up somewhere else, and it will all continue to work with a little bit of delay. So we have this distribution concept built in, and we have this temporal decoupling concept built in. We also have an internal thread pool already sitting there for you, and you can control the size of this thread pool. So depending on your business logic and whatever that your outbound network I/O allows you to do, you can configure this in a multi-threaded way, and you can operate nicely. So this is ideal for this environment. And furthermore, we are very, very, very persistent when it comes to retries. The first level of retries that we have is in the two Azure transports themselves. Okay, the transports themselves will actually perform retries internally. Then on top of that, we have the first level retries done by end service bus. And when those fail, we have another system called second level retries that will retry after a while. We handle all of that. So we are persistent in trying to get your message processed, even in the case that service is actually pushing back on you. These two different transports that we have available are called the Azure Service Bus Transport and the Azure Storage Transport. One is using the Azure Service Bus service in the environment, and the other one is Azure Storage construct that we're using. Now, how do we choose between these two? That's a question I get like every day, and it depends. It depends on what you want or what you need for your application. If you go for the Azure Storage Queues Transport, then it's an extremely reliable service. What do I mean with extremely? Well, it can even survive a meteor crashing into Amsterdam and taking the entire rest of Europe away. There is a copy of all your data in Dublin. Okay, and inside the data center itself, there are also 3 copies of the same data. So you have 3 copies in Amsterdam and you have 3 copies in Dublin. Same here in West US. You have 4 data centers in North America, and those are paired 2 by 2. I think East and West are paired, and North and South are paired. Okay, so if any of these data centers is gone, your data is still there, and it will fail over to the other one. This obviously takes a little bit of DNS redirection and some throttling and backing off while it's moving you, but it actually will work. It's also extremely cheap. It's something that no matter how much data you put in there, you will not even notice it on your bill. Just a single machine will dwarf it. Okay, we're talking cents per gigabytes or cents per million messages. Okay? It's almost nothing. Capacity limits are also huge. The first number you can ignore now because it's no longer valid. The current storage accounts are limited to 500 terabytes each. And I think with a normal account, you can get up to 20 of those storage accounts. So you start counting. And if you call the help desk, you can actually, I think, up to 1,000 or something of those things. So there is basically no limit for the majority of use cases. One of the downsides of this thing is that it's HTTP based. So it has a lot of latency involved by default. It doesn't use transactions. It doesn't support transactions at all, but it replaces transactions with another mechanism to emulate them. Okay, it's called queue peak lock. And the basic way that this works is a endpoint or a node grabs a message and will take a lock on that message. So the message still exists on the server side, but it's temporarily locked. This is a lock of 30 seconds by default. Okay. If the endpoint is able to process the message within that time frame of 30 seconds, then it can also delete that message physically, which basically boils down to a commit. Right? I am done. If for some reason the endpoint fails, to process it in the 30 seconds. That could be an exception. That could be the node that gone down. That could be a network partitioning issue, whatever, right? Then the Azure storage infrastructure will make the message available again for the other instances of the same endpoint to be picked up. Okay. The benefit of this is that under normal circumstances, this will look like a transaction. It will either commit, meaning the delete of the message, or it will roll back, okay, by bringing the message, making it visible again. In some circumstances, it actually also leads to bugs in your application, because if it takes longer than 30 seconds to process a message, then a second one will pick up the same message and also start processing it. And you have the same logic executing in multiple instances of your handler at the same time. Okay, so it's tricky and it's very useful at the same time. What you also need to take into account in this one, even though it's a storage construct, you cannot actually store stuff in there for a long time. Right? The TTL of these messages is a maximum of 7 days. After 7 days, they will be automatically removed. Very important for your audit queues and error queues. Right? If you have audit queues and error queues in this infrastructure, make sure to read them out and put the data somewhere else. Right? That's important. It's very nice, very reliable, very cheap, very easy to use, and has only a few drawbacks. Okay? But it's not very feature-rich. And that's where the other one comes into play. This is Azure Service Bus. I call this highly reliable. It's built for reliability internally, but it does not fail over to other data centers. It supports queues, topics, and subscriptions, so it has a lot richer programming model than Azure Storage. Capacity is a lot less, only 5 gigabytes per queue max. Okay, still a lot for small messages, but you need to take it into account. There is no limit on the TTL here. So you can leave data in your audit queue. It will be there in 5 years. As long as the audit queue is not full, you're fine. Okay. It's also TCP-based over HTTP-based. It can continuously keep a connection open, which will make it a lot more responsive than the HTTP one. Okay. It will immediately give you data. It also uses the queue peak lock mechanism for retries. So again, no transactions. And it has lots of additional features. That's on the second slide after this. Downside, it's relatively expensive. It costs $1 for 1 million messages. It's still cheap, but if you have a high load, it adds up very quickly. You know, it depends on your use case. The additional features and how they're usable in context of end service bus, or one, duplicate detection is very interesting. Okay, within a certain time window, it can actually detect duplicates for you, so you don't have to implement your code idempotently, except if you're running multiple nodes, of course. Right. Partitioning can be used internally to get a lot more throughput on logical queues. You can enable message ordering to maintain the order within the queue. You have dead lettering options, which is not the same as our error queues, but similar in some way. And you can do batching, so you can get a lot more throughput on a single unit by using batching. There is also a feature called sessions, but that's not applicable in the end service bus context because we use the data bus feature for that specific use case. It's intended to route a set of messages to a single endpoint. Okay, so that you can split a file into a message stream basically and all send them to the same receiver. But we do it a different way, so don't use sessions. So there's also the cost model. The way that we and service bus developers typically design systems is to spread stuff all over the place. We have endpoints per handler very often even. If you translate this to the Azure model, you will be poor very quickly because one Visual Studio project will translate to a role, and a role will translate to at least 2 virtual machines. So if you start counting, for every endpoint that you will have 2 virtual machines by default. If you have 12 endpoints, you will have 24 virtual machines running with $60 each. Okay, so that adds up. We are also covering that. We have a shared endpoint hosting model in the Azure bits that you can actually use to have one machine host multiple endpoints. It will download them from the storage infrastructure and host them locally. You still want 2 of those because the machines can go away, but you can at least combine all of your endpoints on one machine. And then if you need scale out later, you can put them on individual machines if you like. Okay, so you're not limited there. Don't put anything on your disk. I'm going to repeat it again. If you ever lose your SharePoint database because you put it on a cloud service, it's your own fault, okay? It shouldn't happen. Put stuff in Azure Storage Services instead. Important there is a difference between some services. For example, the Azure Virtual Machines service, it actually automatically keeps a copy of your disk in Azure Storage. And when the machine gets booted up somewhere else, it will download that copy and put it on the machine again. So in this service, it will look like your disk is persistent. Okay, so you can choose that. It depends on whatever that you need. Of course, you also need to go to it, and Service Bus cannot take everything away. We still have a requirement for idempotent implementations in many cases. Keep them as small as possible. Also remind that if you use sagas, the sagas themselves have state that is being written to storage, and that's also in its own transaction, its own atomic operation. So you should not do any local operations to, for example, storage in the same handler as your saga is. Okay, just spin off a message and do it on another handler. This is best practice anyway, but I know a lot of people sin to this, and don't do that. Now, if you want to coordinate compensation logic, you can also use sagas. And you also seen how Jimmy used the routing slip for the same thing. Okay, those are patterns that you can use to actually overcome those issues. You can also validate retries. So if you have seen a message ID before, you can check that and ignore the message. Okay? And you can have side effect checks. There is a lot of things. There are many more ways to actually get to an idempotent operation. I have a specific documentation topic on that. It's a very long one that gives you all of the different options to build something idempotently. Okay, so definitely check that one out. All right, that's it. You can get started on this your own. This is the documentation. There is a lot in there. It's not always that easy to find yet. We should try to group it a little bit, but it's all available on the documentation side. And we also have samples for all of the combinations available. So we have samples for storage queues. We have samples for hosting it on-premise, but still using an Azure transport. We have samples for Azure Service Bus. And we also have samples for that shared hosting environment. So you should be able to try all of these things out if you want to give it an experiment. All right. Great, thanks. I hope you've learned that the cloud has a lot of benefits, also has some drawbacks, at least in the way that you need to think. But in Service Bus can really make life agréable in French, so it makes it lovely inside the cloud. You only have to think about idempotency most of the time, and the rest is covered for you.